Hello students, welcome to EPG Pathshala. I am Dr. Devrat Mishra from University of Delhi. Today we are going to talk on module Electronic, Magnetic and Optical Properties of Materials under the paper Magnetic Properties Lecture 7. After the completion of this module, you should be able to understand the soft magnetic materials, iron silicon alloys, amorphous and nano-crystalline alloys, nickel iron alloys, AC applications. Soft magnetic materials. Most of the magnetic materials of industrial interest are ferromagnetic materials. The ferromagnetic materials can be categorized into two. One is soft magnetic materials and another is hard magnetic materials. A ferromagnetic material with the demagnetized state does not show magnetization, although they have spontaneous magnetization. This is because the ferromagnetic materials are divided into many magnetic domains. Within the magnetic domain, the direction of magnetic moment is aligned. However, the direction of magnetic moments varies at magnetic domain walls so that it can reduce the magnetostatic energy in the total volume. In the demagnetized state, total magnetization is cancelled because of the random orientation of the magnetization in magnetic domains. When external magnetic field is applied, domain walls migrate and disappear when all magnetic moments are aligned to the direction of the magnetic field. When all magnetic domains are wiped away and magnetizations are all aligned to the direction of the magnetic field, magnetization is saturated and is called saturation magnetization. Soft magnetic materials are those materials that are easily magnetized and demagnetized. In other words, when domain wall can easily migrate, the ferromagnetic material can be easily magnetized at low magnetic field, and this type of ferromagnetic materials is called soft magnetic material. Soft magnetic materials are suitable for applications of magnetic cores or recording heads. The main parameter often used as a figure of merit for soft magnetic materials is the relative permeability mu r, where mu r is equal to B over mu 0 h. It is a measure of how readily the material responds to the applied magnetic field. The other main parameters of interest are the coercivity, the saturation magnetization, and the electrical conductivity. Since soft magnetic materials can be demagnetized at low magnetic field, their coercivity is low, which is less than 1000 ampere per meter, whereas permeability is high, that is initial permeability is of the order of 10 to the power 2 to 10 to the power 5, and maximum permeability is in between 10 to the power 3 to 10 to the power 6. For the ferromagnetic materials to sustain as soft magnetic material, their magnetocrystalline anisotropy and magnetostriction constant must be low. In addition, for easy migration of magnetic domains, they must have small number of defects such as crystal grains. There are mainly two categories where the applications of soft magnetic materials exist. One is DC, another is AC. In DC applications, the material is magnetized in order to perform an operation and then demagnetized at the end of the operation. For example, an electromagnet on a crane at a scrap yard will be switched on to attract the scrap steel and then switched off to drop the steel. For DC applications, the main consideration for material selection is most likely to be the permeability. In case of AC applications, the material will be continuously cycled from being magnetized throughout the period of operation from one direction to another, for example, a power supply transformer. For AC applications, the important consideration is how much energy is lost in the system as the material is cycled around its hysteresis loop. The energy loss can originate from three different sources. Number 1, the hysteresis loss, which is related with the area inside the hysteresis loop. The hysteresis losses can be reduced by the reduction of intrinsic coercivity, with a consequent reduction in the area content within the hysteresis loop. Second is eddy current loss, which is related with the generation of electric currents in the magnetic material and the related resistive losses. The eddy current losses can be reduced by decreasing the electrical conductivity of the material and by laminating the material, which has an influence on overall conductivity and is important because of skin effects at higher frequency. The anomalous loss, which is related to the movement of domain walls inside the material. The anomalous losses can be reduced by having a completely homogeneous material within which there will be no hindrance to the motion of domain walls. As we have seen in the figure 1, the hysteresis for soft ferromagnetic material. The coercive field is very small. As a result, the magnetization can easily switch from one direction to the other direction with an application of a small field. These alloys are used for transformer cores and are known as electrical steels. In the power industry, electrical voltage is almost always AC and at low frequency 50 to 60 Hz. At these frequencies, eddy currents are generated in the transformer core. Alloying the iron with silicon has a large marked effect on the electric resistivity of the material, with an increase of a factor of 4 for 3 weight% of silicon. Silicon also has the benefit of reducing the magnetostriction, that is, length change on magnetization, and the magnetocrystalline anisotropy. In addition, the material is used in the form of lamination, typically 0.3 to 0.7 mm thick. The addition of too much silicon makes the material extremely brittle and difficult to produce, giving a practical limitation of 4 weight% to the amount of silicon that can be added. Recently, a technique has been developed to produce lamination with greater than 6 weight% of silicon by a silicon SiCl4 chemical vapor deposition treatment to enrich the lamination with silicon after forming the laminations. Typically, most electrical steels will contain between 3 to 4 weight% of silicon. For transformer applications, the flux lies predominantly in the length of the laminations, and therefore it is desirable to enhance the permeability in this direction. This is achieved by various hot and cold rolling stages to produce textured sheets known as grain-oriented silicon steel with the 001 direction in the length of the lamination. The 001 type crystal directions are the easy direction of magnetization and hence the permeability is greater. The anisotropy of iron can achieve two types of textures, which are known as cube on edge and cube texture. Amorphous and nano-crystalline alloys. These materials can be produced in the form of a tape by melt spinning. The alloys consist of iron, nickel, and or cobalt with one or more of the following elements: boron, carbon, phosphorus, and silicon. They have extremely low coercivity, an order of magnitude less than standard iron silicon, and consequently lower hysteresis losses. However, they have relatively low magnetization and are not suitable for high current applications. They do find a market in low current applications and specialized small devices where they can compete with nickel iron. Instead of casting the alloy onto a rotating wheel to produce tapes, it is also possible to squeeze a stream of molten alloy into a bath of water or oil to produce amorphous wires of typically 50 mm thick. These wires show a very square hysteresis loop with large changes in magnetization at low field, making them ideal for sensing and switching. Recently, there has been much interest in nanocrystalline material, which is produced by annealing the amorphous material. These alloys can be single-phase but are usually comprised of nano-sized grains in the range 10 to 50 nanometer in an amorphous matrix. They have relatively high resistivity, low anisotropy, and good mechanical strength. Nickel-iron alloys. These alloys, known as permalloy, are extremely versatile and are used over a wide range of compositions, from 30 to 80 weight% of nickel. Over this composition range, the properties vary and the optimum composition must be selected for a particular application. The high nickel content alloys have high permeability. Around 50 weight% nickel have high saturation magnetization, and low nickel content have a high electrical resistance. There are special grades of nickel iron alloys that have zero magnetostriction and zero magnetic anisotropy, such as mu metal, which is produced by a careful heat treatment and minor additions of copper and chromium. These alloys have extremely high permeability up to 3 lakh and intrinsic coercivity as low as 0.4 ampere per meter. AC applications. AC applications relate to electric circuits and primarily in transformers converting one AC voltage into another. Power transmission is more efficient at high voltage but more dangerous when and is less easily used in home. Therefore, step-up transformers are used to increase the voltage for transmission, and step-down transformers are used to reduce the voltage before entering the home. The smallest type of transformer is a DC-DC converter, also known as a switch mode power supply. These are often mounted on a chip that can be put onto a circuit board. They take a DC voltage input, oscillate the voltage to an AC signal, which then goes through a coil around a toroidal core. A pickup coil picks up the signal from the core and rectifies it to the output voltage. The relative number of turns on the primary and secondary coils determines the difference in voltage between input and output. Soft magnetic materials also play an important role in electric motors, where they enhance the field produced by the motor windings. In permanent magnet motors, they are also used to channel the flux produced by the permanent magnets. Amorphous solids consist of a random aggregate of atoms whose atomic positions are strongly correlated in the nearest neighbor cell but uncorrelated beyond a few atomic spacing. In other words, these materials possess short-range atomic order, and the structure of these solids resembles that of liquids from which they have been obtained. Molten metal and metallic alloys invariably crystallize in their equilibrium crystalline structures when cooled below their freezing points. Dweck and his co-workers were the first to synthesize amorphous metallic alloys by a rapid solidification technique. This pioneering work initiated a spurt of research activity on synthesizing and exploring the exciting new phenomena exhibited by various amorphous metallic alloys. Amorphous alloys can be obtained through two diverse routes. One is rapid solidification, for example melt spinning, and mechanical alloying. Rapid solidification is a non-equilibrium process and is based on the principle of cooling the molten alloy fast enough and far enough. In this process, the molten alloy is not permitted to crystallize and made to solidify into a metastable state. Most of these metastable or supercooled liquids exhibit a glass transition and hence are also referred to as metallic glasses. In the melt spinning technique, the molten alloy is ejected through the orifice at the bottom of the tube by pressurized argon gas onto a water-cooled copper wheel rotating at a high speed under argon gas atmosphere. This process provides a fast cooling or quenching rate for the molten alloy of the order of 10 to the power 5 Kelvin per second. On the other hand, mechanical alloying technique is a complex process involving deformation, fragmentation, cold welding, and micro-diffusion of elements in the solid state in a highly energetic grinding media. One of the main advantages of studies on amorphous alloy is that one can vary the composition continuously to prepare homogeneous alloys, which can be studied without complicating interference from the structural phase transitions. A special class of amorphous metallic alloys, particularly known as bulk metallic glasses, can be synthesized from the melt with very low cooling rates. BMG are not discussed further since this is focused on soft magnetic materials which can be obtained only by rapid solidification or mechanical alloy techniques. There are four technologically important classes of magnetic amorphous alloys. One is transition metal, metalloid, early transition metal, late transition metal, rare earth transition metal, and alloys with group second A elements. Magnetism in LTM ETM amorphous alloys has been extensively investigated from both fundamental and technological points of view. Also, considerable efforts have been devoted to the understanding of systems with frustration arising either from competing exchange interaction or from random magnetic anisotropy. Many alloy systems with competing exchange interactions show novel phenomena such as double magnetic phase transition behavior, invar effect, resistivity anomalies, and magnetocaloric behavior in the amorphous phase. Furthermore, these alloys in nanocrystalline state exhibit outstanding soft magnetic properties such as ultra-low coercivity, high saturation magnetization, and high permeability. Hence, these alloys have been a fertile ground for the exploration of novel magnetism. It is well known that the general composition of such alloys is LTM-ETM-M, where LTM is generally body-centered cubic BCCFE in the range 50 to 93 atomic percent. ETM typically consists of zirconium, niobium, hafnium, etc. The nanocrystalline materials can be obtained through controlled crystallization of amorphous precursors and mechanical alloying technique. The obtained nanostructure powders from mechanical alloying consist of particles composed of nanometer-sized crystalline grains linked one to another through grain boundaries, but highly refined and strained. These nanocrystalline materials find wide applications primarily for high-performance magnetic parts such as in electronic devices, common mode choke coils, power electronics, bead cores, noise absorbers, magnetic switch cores, transformers, current sensors, and electromagnetic shielding. Apart from the soft magnetic applications, these materials are used as magnetic refrigerants based on the principle of magnetocaloric effect and are also used in magnetic impedance purposes. Conventional methods of improving the intrinsic and extrinsic soft magnetic properties have been focused on tailoring composition, control of microstructure with heat treatment under different environments, reduction of Hc, that is coercivity, increase of saturation magnetization Ms, and control of intergranular exchange coupling in the amorphous and nanocrystalline materials. Cobalt substituted iron cobalt zirconium boron alloy generally falls under the generic name heat form. Addition of cobalt in iron, cobalt, zirconium, boron alloys increases coercivity, saturation magnetization, and Curie temperature Tc, but lowers the crystallization temperature. In addition, the small amount of cobalt addition helps to optimize the magnetostriction properties as shown in figure below. Lorentz microscopy coupled with focused ion beam was used by Saito et al. To investigate the effect of high cobalt addition in the magnetic domain structure of iron, cobalt, niobium, silicon, boron, copper alloys, and to obtain the relation between the induced magnetic anisotropy and magnetic domain structure. However, high cobalt addition in iron-based alloys restricts the crystallization process due to exhaustion of Fe in the amorphous matrix. Recently, it has been shown that the structure of cobalt-rich nanograins can be tuned by means of static magnetic field annealing. Similarly, rotating magnetic field annealing helped to reduce coherence uniaxial anisotropy, and the reduction in Hc value was observed for nanoform alloys due to the decrease of fluctuating amplitude of the effective anisotropy. On the other hand, the addition of manganese in iron-cobalt based alloys not only shifts the crystallization temperature to higher temperature but also helps to enrich the nanocrystals with iron and cobalt. Also, the partial substitution of manganese in iron-based alloys such as fine matte, nanoform and heat-form alloy has been a subject of great interest. Interestingly, the substitution of manganese in iron aluminum alloy powders prepared by mechanical alloying process reduces Hc considerably in contrast to the behavior observed in melt-spun ribbon alloys. However, no systematic studies have been reported on the temperature-dependent magnetic properties in these alloys. Magnetic field annealing helps to induce uniaxial anisotropy in iron-based nanocrystalline soft magnetic alloys. Thus, the microstructure, magnetic domain structure, and resulting magnetic properties can be tailored for suitable applications. However, the questions related to the influence of nanocrystalline microstructure on magnetic domain structure and magnetic properties of iron, cobalt, manganese, zirconium, boron alloys with zirconium atomic percent greater than 7 content prepared by different synthesis routes are still open because of the complexity of the problem. Also, understanding how magnetic properties are optimized in conjunction with the microstructures and domain structures would be useful for designing high-performance nanocrystalline materials. Detailed investigations of microstructure, temperature and field-dependent magnetic properties, and the evolution of room temperature magnetic properties of cobalt and manganese substituted amorphous iron zirconium boron alloys having high zirconium content have not been reported. Hence, investigating the influence of additive elements such as boron, cobalt, and manganese in iron zirconium alloy powders and ribbons prepared by mechanical alloying and melt spinning techniques is important. So students, let's now summarize what we have learned in this module. So we had a brief description of magnetic materials along with the application of iron silicon alloys, amorphous and nanocrystalline alloys, nickel iron alloys, and AC applications is explained in this chapter. Thank you.